Okay, hi everybody. Welcome to this webinar on improving your ship design processes with faster hydrodynamic simulations. Before diving into the webinar topics, let me briefly give you the context for this webinar before I show you why your next environmentally friendly ship design is closer than you may think. The ever-increasing pressure on the commercial market to reduce emissions, you need to make radical engineering decisions faster, and for that you need simulation tools that are fast, easy to set up complex problems, can be automated, and allow you to embed best practices that can be shared across your organization and help accelerate your productivity. Once the right tools are in place, only then can you start to consider hundreds or even thousands of trade-offs and designs early and often in the development process, which will then allow you to stay ahead of your competition with innovative designs and better performing vessels, all while reducing your cost and time to market. And of course, you always want to work with real case scenarios, like you see here, this example of a novel concept called sea bubbles, with these videos being provided us by the courtesy of Campinetto Huber. Now, I wanted to take a deep dive into the enabling technologies behind the simulations we just saw. Let me introduce myself. My name is Miles Wheeler, and I'm a Senior Marine Application Specialist here at Siemens. I primarily focus on the use of SimCenter Start2Sim Plus for the maritime industry. And I want to thank everybody for taking the time to attend this webinar. And I think we have some exciting stuff to share. And I hope you will gain some benefit out of it and learn something from the time that you're spending with us today. But before I dive into all of our fancy CFD technology, I wanted to first take a step back and think about how parts are manufactured. How long does it take to create a part? How precise can the tolerances be? And how have we gotten to our current state of manufacturing? Because if you think about it, back in the beginning of time, we would create things by hand building them. We'd use very rudimentary tools, and blacksmithing was how it was done many, many years ago. And while we could have made useful things, it did take a ton of brute force manual labor. And while the parts were functional, they certainly were not precise as they could be, and they took a very long time to make. But then, of course, over the years, we improved our processes by creating tools and machines that have allowed us to produce things with very high tolerances in repeatable fashions. So long as a skilled machinist or fabricator was driving the process. With these skills and tools, we were certainly able to make better quality parts with quicker turnaround times in more repeatable manner. But now let's think about where we are in today's landscape. We have automated machines that can CNC or 3D print parts directly from CAD files with the touch of a button, which allows us to produce very high precise, novel parts that were unattainable or perhaps even unimaginable just a few years ago. We can produce these parts very quickly without the need for a highly skilled technician to drive the process. And I brought this up because parallels from the manufacturing world can be drawn to your simulations today. In the early days, we could build models by hand in a similar brute force manner. Hand meshing was the name of the game, and we would build models for months to run a case, with the effort of allowing one to gain some small insights into the respective design. Then, over the years, tools have been introduced that make it easier than ever to create your simulation models. Surface wrapping, automated meshing, pipeline workflows. The advancements in available tool sets allow people to build highly detailed models much more easily and quickly. But it still required a highly knowledgeable CFD expert to build and run these models. Although the simulations were easier to build, they did take days and days and days to run. But what if I told you we were at the turning point to the next step? Automated and faster workflows, complex simulations with the touch of a button. Well, that is what the focus of this presentation is about. And I plan to focus on how you can get better information and increased realism out of your simulations, all while speeding up your simulations from weeks to hours while using easy to use templated setup files in our latest technology. To illustrate my point, I first want to walk through what most people would do to to set up a standard case or ship resistance case in a CFD tool. First, we have to import the CAD model. We have to ensure it is orientated correctly. We need to confirm the quality of the CAD. Then we have to determine or apply the mass properties to ensure the model is placed just so in order to have the simulation run smoothly. We have to determine the hydrostatic properties such that the hull center of buoyancy is aligned with the center of gravity and is displacing the appropriate amount of water. Then we have to think about how to build our mesh. For marine cases, we have to think about how high the generated waves will be, the proper mesh transitions, and where the generated wakes will be. This can be a cumbersome process with several hand calculations and typically about a dozen boxes to create the settings and capture all aspects of the model appropriately. But not only that, we also have to worry about what is going on the boundary layer and the appropriate way to capture it. What are the appropriate Y+ settings? How can we smoothly transition the prism layer into the core mesh? What is the appropriate cell size for this model? How can we build a mesh that is accurate but also runs quickly? And this can take several iterations and often requires a lot of thought. Then we need to think about the physics of our problem. We need to set up the solvers. We need to think about what type of turbulence models we want to use. What is the appropriate time step? We need to determine how to set up the free surface conditions and how to apply all of the relevant boundary conditions. But what if instead, all you had to do was input the CAD, set the draft and speed, perhaps add a propeller, and that was it? Well, SimCenter StarSystem Plus now has the full capability to take out most of the manual processes involved with building a CFD simulation via our parameterized template modeling capabilities. What we have here is what we call the VTT template, which allows a user to automatically run a resistance or self-propulsion analysis at any scale with just a few inputs and clicks of a button. SimCenter StarSystem Plus has the ability to parameterize most things in the tree. And if you think about it, most of the meshing and pre-processing decisions for a ship are based on this geometry, the speed, and the displacement of the vessel. With the addition of these simulation operation tools we have in SimCenter StarSystem Plus, all of these calculations and thought exercise can be completely embedded and automated without the need for any scripting and embedded completely into your simulation template. Here's an example of how it works. When we open up the template, we get a custom tree as well as an instruction scenes that allows you to tell you exactly what you need to do. You can navigate and import your hull geometry and will import into the scene. We'll then give you the dimensions of this part and you can easily scale it if you want to go from full scale to model scale or model scale to full scale. And all the relevant input properties are displayed in the scene. We then have a few different options. We can have a full model or a half model, so you can assume symmetry or not. You can input the properties of seawater via a table, or freshwater or seawater via a table, or input them directly. And then we set the draft and we set the speed that we want to analyze. If we want to run a self-propulsion calculation, it's just simply setting a parameter that says, yes, let's include the propeller. And here we have what we call a virtual disk, which allows us to mimic propeller behavior with the use of open water propeller curves. And of course, we can then import those curves and change the dimensions of the propeller as needed for the particular problem. We can move its location and change its diameter and inner hub radius if we need to, as well as change the propeller rotation. And as you see, we really simplified the tree. We can reduce the inputs, the model tree that is exposed to the user, just to the inputs needed for the model. And once everything is input, just a few different inputs to set up a self-propulsion calculation. We run through these simulation operations, and that's it. All of your pre-processing, meshing, running, solving, and post-processing steps are automatically executed for you. But what's even better is the template is completely open, which means that you have access to all the controls you normally would if you built the model by hand in our commercial product. So if you and your company have any secret sauce or you want to embed your best practices into your file, you can do so. It doesn't require any new release, doesn't require a new script, doesn't require anything else except for you to go in and change it on your own. You can make the change just as you normally would, and then you can continue using your template in the same manner. This is not a black box solution. It's completely open and transparent, and you have the ability to edit and do these templating steps yourself. Then, whenever you reload the model, as I mentioned, you can expose just the key inputs to the tree. This helps you ensure that the best practices for your organization will automatically be populated and used, which will then ensure better quality control of your simulations and less time spent on policing others' work, because people aren't going, when they're working with this tree, they're not going in, they're not changing solver settings, they're simply changing the boundary conditions of the model, and everything else is done exactly the same way, regardless of who is using the file. And then one thing I also wanted to point out is while we showed the manual setup process, the template can also be run in batch mode, which means that you can take any of the boundary conditions or perhaps even have your look at different hull files and set those up to be a parameter. And then that gives you a one-click solution to go from your CAD to your resistance or propulsion or powering calculations. And it doesn't have to be a walkthrough wizard if you don't want it to be. You can have it be a one-click solution executing in batch. And with the use of our design manager tools, you can do design explorations on hundreds or even thousands of designs, all with the same template file without having to even interact with it or open it if you don't want to. Now, you may be thinking to yourself, that's great. The template saved me some pre-processing time. You have probably done something similar or have even seen templates before. But it still takes several hours to run a simulation. The pre-processing time is, perhaps just a fraction of the total time it takes to get a CFD result. Well, that's actually, in my opinion, not necessarily true anymore. I want to introduce you to two additional technologies available in SimCenter StarCU Plus that will allow you to make your runtimes even faster. First one is multi-mesh sequencing, or MMS method. The MMS method is simple. You define a final target mesh for your simulation. This is automatically defined in the template file. However, to develop the flow field, it can be cumbersome to have to do this on a very large mesh. So why not just do this on a coarse mesh with less cells? Well, we can. So by using this coarser mesh, we can develop the flow field and wake structure much, 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 much faster. We can then converge the mesh and map the solution to a slightly finer mesh and repeat the process. We can repeat the process until we get to our final mesh. We do that until we reach our final target mesh. And by doing this, we can save a lot of time of continuously using finer and finer grids while we develop the flow field, and only using a detailed grid once we have an almost converged solution as the initial condition. The best part of the method is that it uses simulation operations to automatically do this process. This means every setting is determined and embedded directly into the sim file, which means that the MMS method is script-free. And we have extensively tested the MMS method against our previous best practices for several different cases. One such case is the benchmark Lloyd Register blind CFD benchmark case. And I wanted to point out a few things. First, the workshop is publicly available, so we can compare data freely. In this benchmark, we analyzed the resistance versus speed curve in CommWater for over 4 speeds. And we compared the median of the workshop data to our previous best practices and our MMS method. There's really no difference in the results in the MMS method, and the difference between the median is that it's a statistical based on submitted results. It's not actually comparing to any experimental data. And when we actually did this benchmark, we noticed that the results from the MMS were over 2 times faster, and they're actually even faster on other cases, typically on the order of 4 times faster. So we have a very nice method that can be implemented completely within the simulation that has a significant speed up. This means you can either analyze over twice as many designs in the same amount of time, or perhaps only spend maybe half as much time in the office if you could get away with it. But this brings me to our other addition, adaptive mesh refinement. Adaptive mesh refinement, or AMR, is another approach we have to making your simulations faster. AMR was just introduced into the code a few years ago, and we were very excited about it. AMR is a solver-based mesher that will refine and coarsen the mesh as the solution converges. This allows you to focus mesh in areas where you need it and allow you to have coarser meshes in areas where you don't. We can create any refinement operation with any of the field variables stored in your simulation. But I wanted to point out two very useful model-driven applications for the marine industry that are unique to our software. First, our proprietary free surface model is being used to track and refine the free surface. The animation is not working in the PowerPoint, so let me pull it up really quick. It is here, so you can see that the free surface AMR is actually refining the head of the free surface. So that allows us to always have a nice crisp free surface as the solution develops. It's unique to our software. And it really allows you to maintain a crisp mixture with much fewer cells. In addition, an overset mesh adaptive refinement scheme has also been implemented. What this does, it allows you to build very coarse background regions, and the adaptive mesh refinement will only refine in areas around the overset mesh. This will also help eliminate any of the overset errors you might typically encounter in these types of simulations. In this example, we can see a simple vessel maneuvering within a basin. On the left, you will see how we would typically have to create this case previously with the expected path of the vessel. But now, overset AMR, we can leave a coarse background and we only need to refine as the object kind of comes in contact with the background region, saving you a ton of cells and overall will save you a ton of time. But even better, in my opinion, is it takes the guesswork out of predicting where the vessel will go when you have highly dynamic cases. And it allows you to also eliminate a lot of the overset errors you would get when trying to match cell sizes between the object and the background region. So overall, a very robust solution that saves you a lot of time. And in this particular case, we had 3 times fewer cells, which gave us 3 times speed up for the same exact case with very similar results. Then we employed these 2 adaptive mesh techniques and we applied it to a previous simulation we had trouble with. With AMR, we were able to focus the mesh in areas where we needed it. And in this video, you can see a planing craft accelerate from rest to a steady state position with the use of our free surface and overset refinement implemented here. The particular case is one where we had a strict computational resource limit. The customer did all of they could to get decent results, but the results were not coming out well due to their computational constraints. Their original mesh was nearly 5 million cells, but the results were not very good since they were experiencing numerical ventilation, which is when air isn't trained directly underneath the hull, strictly due to too coarse of a mesh. You can see the mesh in this image of the problematic case. They used the consistent cell sizes across the bottom of the hull, since they did not previously know where the spray root lines would be on the hull. This is a standard way of addressing the problem, but due to the CPU constraints, this was as fine a mesh as they could create. And we were able to help solve this issue with the use of AMR. In this mesh, you can see the coarser mesh was used as the base size, but the AMR algorithm intelligently finds the spray root line and focuses the mesh refinement there. The result is a significant improvement in the numerical ventilation. The results are significantly better. Not only that, but there's also a 2.7 times improvement in the simulation time. Now that I showed you templates and our latest in technology to show, the latest in our technology to speed up your simulations, I want to point out that SimCenter StarSystem Plus is completely built from the ground up for design exploration. We have integrated CAD to solution in a single platform. We can link directly to most CAD packages and update designs from within our tool. We have robust and automated meshing, as well as pipeline and replayable workflows with our solution templates, as I just demonstrated. So what does this mean? I'm talking about running hundreds of simulations at once to find the best compromise and trade-offs in the design. In this case, we're changing the design features of the hull for an offshore supply vessel by varying 14 hull parameters, looking for designs with smaller resistance, which ultimately result in improved performance. And with the right choice of hull parameters, note that the breadth of design and hull shapes that we are looking here. And after variations have been explored, we see that we've achieved a better design where we started, a full 33% reduction in resistance, and significantly improving the hull performance. And this is what I mean when we talk about design exploration. I now want to walk you through a design exploration case that we recently did, in which we can go from weeks typically needed into getting all of your data in just a few hours. Here we have what we call a multi-role vessel. This is a Siemens demonstrator vessel. It needs to be able to operate at several different drafts and speeds. As such, a full understanding of the powering or resistance requirements are needed over a range of drafts and speeds. Particularly, we need to understand the performance between 5.5 and 7.5 meters in draft, as well as understanding its operational performance between 10 and 30 knots. Using increments of 0.5 meters in draft and 2 knots, this would mean that we would need 55 different CFD simulations to generate the performance curves for these operating conditions. And traditionally, this might sound a bit problematic. A single data point would take several hours, a full data set for a vessel would take several days, and the full resistance profile over multiple displacements would take weeks to do. However, with cloud computing, our design manager tool, and the power of our on-demand licensing, we can run all these cases while we're at lunch in just under an hour. So let me show you how to do it. I just demonstrated how you might be able to speed up and automate your simulations. And now I want to talk about how to harness these gains in conjunction with our design manager template file. In this video, I'm going to show you how easy it is to set up a design sweep in our design manager tool. We simply start off with our template. We right-click to get to Design Manager session. And it's worth noting that doing sweeps in Design Manager does not involve any extra licensing costs. Then we can grab any parameter defined within the template. In this case, we're interested in the speed and the draft. We grab those, and then we set up the range of each parameter that we want to do. So here we've selected the parameters, and now we can give it the range that we want. Between 5.5 and 7.5 meters. And we want increments of 0.5 meters. Similarly, we can now input our speed range between 10 and 30 knots. And we want 2 knot increments, which is totally fine. And then we can go through, we can set up our run settings. We want to run these on our Linux cluster, whatever hardware you have available to you. We want to save all of our simulation files, our log files, and we want to run 55 designs at one time. The Linux cluster then tells you exactly how to submit it. That's our submit script. And this will then allow you to run all these designs at once on our Linux cluster. Then with cloud computing, you can get as many nodes as you need. It allows for easy on-demand compute nodes, and you can build a cluster and only pay for the compute nodes as you use them. Once you build a cluster, you can easily copy files and submit the design manager job, and it's easy as just typing in a simple command to submit the file. And then in about 5 to 10 minutes, your cluster will be built. All your jobs will be running. And in 45 minutes here, it actually completed all of the runs. The results are stored in an easy to manage file. We can download the file back to our machine. While we ran very quickly, I also wanted to point out a few other things. We used our on-demand licensing scheme for this particular study. Our Power on Design licensing scheme is varied by the elapsed simulation hour. This means is you are not paying extra to run on more CPUs. You can use all the CPUs you want for your simulation, and the cost is the same. In fact, you'll actually save some money if you run in the most efficient way possible. You'll actually get your results even faster. In this example, I ran on 70 per simulation, and all runs finished between 15 and 30 minutes. And the total cost to perform all 55 runs was under $500 US, and the price per run varied between $7 and $14 per simulation, which I personally think is quite reasonable. And we can look at the file, we can make plots, confirm the results. In this case, it is clear all runs finished successfully. We have all these check marks here. And all the results are stored in an easy to read table, and you can pull up all the plots and images as you scroll through results all within one database. which is what we're going through here. We can look at each individual design. We can see what the resistance is here. We can take a look at the generated wake. We can look at the bow wave. We can look at really whatever metric or visualization we want, all within a single environment, which allows you to really easily understand your results as you go through them. Now, let's switch gears. Now that I've showed you ways to improve your productivity and save time, you will probably have the time to do more sophisticated analyses and increase the realism of your simulations. In the simulation, we have a model test compared to the CFD simulation. Can you actually tell which one is which? It's pretty hard if you ask me. Well, this is a simple example. I wanted to run through several others in which our advanced physics capabilities have helped our customers solve complex problems and add realism into their simulations. The first example I would like to show is some work done by our customer Chitana, who simulated the launching of a procedure with the help of our engineering services team. The ship that needed to launch was the largest ship ever created at this particular shipyard. The size of the ship, the departure angle, and shallow water in the bay had the shipyard worried about a successful launch. There were some clearance issues that were critical to the concern of the propellers and rudders. The shipyard significantly relied on hand calculations that were assumed large margins of error, and these processes were okay, but given the size, it was not possible to rely on these methods as the traditional launch calculation methods were purely static calculations and neglected the following aspects: the free surface deformation or the wave pattern, the interaction with the seabed and the surrounding structures and the quays, any of the inertial effects. Detailed computation of resistance and effects of the appendages and the propulsors were not carried out with these older methods. So with their worries, they needed a more high fidelity analysis. They turned to the SimCenter Starsys Plus and our Siemens engineering services team to help them out. So they ran several simulations with contact, complex motions, appendages, multi-body interactions, and these free surface interactions to try to figure out what set of parameters could produce a safe and successful launch. As you can see, there were some tight clearances on the worrisome part of the bay floor, where the simulation provided enough fidelity and insight needed to figure out what could possibly work. And it was determined that a safe and successful launch was achievable based on simulation. And at the end of the day, the shipyard was able to successfully launch the largest ship it ever produced in some terrifyingly shallow water, not much of an issue. Next thing I wanted to point out is our capabilities of rocket launch combined with hydrodynamic and aerodynamic simulations. Here you can see a YouTube video of a rocket launch by the US Navy. The fumes and flames are very high before the rocket is even launched. And we can simulate the same conditions that include the heat transfer, compressibility, high-speed aerodynamic problems in conjunction with our hydrodynamic capabilities, all within a single simulation. We can see the generated shock waves and how they might affect the important things on deck, such as helicopters, cargo, people, what have you. And we can also look at the plume effects, giving us great physical insight into any type of launching situation. We can see how the gases are dispersed on deck and see if that might affect anything critical on board. The other thing I would like to point out is some of our fluid structure interaction capabilities. We have one-way coupling. We have two-way coupling with SimCenter Nastran and other finite element codes. We also have two-way coupling embedded completely within SimCenter Starsys Plus. This animation, we can see how we can optimize the structure with our one-way coupling techniques. If the wetted surface area remains relatively unchanged, we can map the wave impact onto the structure and optimize the structure using input loads from our design exploration tools. But if the hydrodynamic response of the deformed structure is needed, we can do this with tight two-way coupled FSI simulations. In this animation, we can see how the composite panel is affected by wave slamming. The deflection of the bow could have adverse consequences on the roll and directional stability of this vessel. And this is the type of fidelity insight that can be looked at with our seamless SimCenter Nanostrand and Star CCM Plus two-way coupling offering. There's a socket-based coupling that can link any FEA model with our high fidelity CFD capabilities. But SimCenter Star System Plus also has a 3D solid finite element solver that can easily map with our fluid solver. This allows for seamless FSI integration into a single simulation platform. In this case, we can see how the deformations of the propeller might affect the thrust and the corresponding motion of the vessel. For our advanced FSI capabilities, we can get true realism into our designs by understanding how the structure movement can affect the performance of the vessel in several different scenarios. Another important topic I wanted to discuss was the operation of ships in brash ice. We also have a discrete element method, or DEM solver, within our software, which allows us to include things such as clump particles, as well as the interactions with one another, as well as their interactions with the fluids, can all be modeled together. So in this animation, we can see how these ice chunks are flowing around the hull as it moves through brash ice condition. The ice particles will affect the resistance, and this increase in resistance and required power can be determined. We can also determine if any of the localized contact forces on the ice collisions may impact the structural integrity of the hull here. And of course, with combined with our FSI capabilities, we can also determine both the probability of ice flowing into the propeller and what the stress ramifications will be when the ice comes into contact with the propeller. SimCenter Star System Plus also has the ability to be coupled with SimCenter AimSim, our 1D solver tool. And we have the ability to couple with generic models via our FMU and FMI co-simulation interfaces. In one-wide couple simulations, you can take your resistance calculations and determine the range, the fuel burn, the emissions requirements by incorporating this high-fidelity CFD data into long-range 1D system simulations. On two-way coupling, we can integrate our motor effects into our CFD simulations directly to help understand how the engine, propulsor, and hull all interact together. This can help you solve your time to plane problems with a credible insight or help understand your engine effects in extreme maneuvering conditions. We've had webinars on this topic in the past, so you can please look those up on our webinar website. If you're interested in this capability, I would highly encourage you to take a look, as it really is a unique solution offering from Siemens that can really give you a lot more insight by coupling these two solvers together. And that concludes my presentation. I do want to thank all of you who have attended. I think I have showed you how some of our advanced capabilities allow you to add more fidelity into your simulations. I've demonstrated how we can easily run hundreds of designs in a matter of hours by using our automated simulation templates, as well as our design manager tool in cloud computing. And I hope you will agree that we are entering the next stage of the simulation world. Hopefully you will believe now that anyone can have access to a high fidelity simulation in an automated fashion. And hopefully that will allow you to create better designs and do some very novel and unique things in the near future. So thanks again. If you have any questions or comments, please reach out to me. You can find me on LinkedIn or shoot me an email if you have it. I'm always happy to discuss marine CFD with just about anyone. So thank you very much. Thank you for attending, and I hope you have a great rest of your day wherever you may be. Thank you.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.